Well, Rafał Malewski with VeriSilicon. I'm here with Kyle Fox, Director for i.MX at NXP. And today we're going to talk about i.MX family and the GPUs inside it. So, Kyle, first off, let's start with the i.MX 6.
Sure.
You've had a lot of traction over the years, a lot of penetration within automotive, industrial, consumer as well, and the product has matured over the years. How do you see that whole track record for i.MX 6 going?
Well, i.MX 6, we did a unique thing in there that has helped us in our success in those different markets. One of the traditional ways of building a processor is you want to put graphics in, you put one graphics unit, you send all the traffic to it, displayed on a screen. That is an old way of looking at the model. That's where you maybe have a phone or a tablet as a single screen. Well, everybody knows in automotive and even in industrial and control centers, you have multiple streams of multiple content being used everywhere. So one of the things we did with 6 that marked it as an excellent product for those markets was our triple play architecture. So at the beginnings, and I'll show you how that worked with i.MX later, instead of just doing one GPU, we put in a graphics unit, we also put in a 2D unit as well as an OpenVG unit. And the reason why is we recognized when you're going to display wonderful rendered 3D graphics on a screen, you want to use a GPU. If you're wanting to do text, using OpenVG is a better way of doing that. If you want to do cover flow through the application, 2D is much better than that. So what did that buy us? Well, the main thing behind it is that if you have a user interface that is just doing cover flow of images, you can shut the 3D unit down, save that power, and just use the 2D unit. If you're only displaying text, you can just have the OpenVG unit on it. So you're able to do a continuum of power consumption mapped to the use cases you care about.
That is great. And throughout those years, the product has matured significantly. It's hardened across the various OSs that you support. And when we look at the i.MX 8 that you're showing here, you've chosen the same GPU architecture for that, so the software goes along with it. How do you see that impacting time to market for your customers and the maturity of the product for the i.MX 8?
Well, you hit on two things. So when you look at an automotive and industrial market, it doesn't follow a consumer cycle. We're talking about long years of investment, sometimes 10 years before an actual product gets out. So i.MX 6, we started it with just 3 processors. Today we're on 12. So from a hardening perspective, we've had millions of person hours and millions of lines of code and testing in real products to make sure we've dialed in the software that works with that graphics architecture. So when we went to i.MX 8, it was a natural choice to be able to take the existing architecture and enhance it for what we want, because we're able to build on that baseline. So when it comes to a product where someone wants to make sure that the code and the IP is going to work reliably, and for a software developer who has spent multiple years working on a previous generation, you want to be able to reuse that capability and rely on it in the next generation.
Great. So what we're showing here is the i.MX 8. So for the i.MX 8, you actually chose to put in 2 3D GPUs.
Right.
Yeah. Can you elaborate on why you did that? Because that's pretty unique in the market.
Absolutely, and it really comes from the pedigree we started with the 6 series with our triple play graphics. The way to answer that question is you have to think about, in the automotive case, what are you actually seeing when you step in that car? In a modern day automobile, you're actually, instead of seeing maybe a navigation screen, you're seeing a heads-up display and you're seeing an instrument cluster. Now, when you think about driving, if your instrument or if your navigation display were to crash or have a glitch, you're not going to have a safety issue. You may be annoyed that you get to the wrong place, but it's not going to endanger you as a car. But if your cluster and your heads-up display were to blink and go down, that's a safety issue, especially if the driver looks down and tries to figure out they're no longer looking at the road. So to solve that problem, typically what automotive manufacturers will do, will use a hardened operating system that's hardened for crashes and failures and recovery on the cluster and HUD, and use a more consumer-friendly operating system for the navigation display and the applications that run there. Now, if you're going to run 2 operating systems on a chip, one of the ways to do that is to make sure that you have independent graphics processing and display processing units. That way, the hardened OS has its own graphics processor, its own display processor. The navigation system has it as well. That way, you don't have to use software to mix them together to try to guarantee safety. We're literally isolating the subsystem, so if that navigation system has a problem, this system will stay up regardless.
Cool. That's very good. And is that what you're showing here on the demo as well?
Absolutely. In fact, I'll start it off for you. This is a representation. This is actually a live demo. It's running off of our i.MX 8 Quad Max application processor. It's our development platform. What we're showing here is a heads-up display and a digital cluster, as well as a navigation screen where all of our route information is handling.
Yeah.
So I mentioned the split architecture. One GPU and display is running an operating system to drive the heads-up display, which is your direction of look. You also can glance down at your mileage, gas, what gear you're in, and where you're going. And this is a screen that is replicated off of the second unit, which is running on its own separate operating system, its own separate GPU. So this is an example of e-cockpit. So we're moving to a world of all glass within the car. Every single surface is going to have some sort of digital display, and this is in action. So the way to look at this is we have 3 independent screens of content running simultaneously with independent content, independent context on 2 different operating systems and running at very high frame rates.
That's really great. And i.MX has typically been and still is a product that doesn't just cater to automotive. So do you see the dual GPU architecture also fit within the other markets you're targeting?
Absolutely. So if you look at this from the rise of machine learning and edge computing, one of the things that a split GPU architecture that lends itself is to machine learning, whether it's in the car or an industrial environment or a consumer environment. And the reason why is, if you want to have a screen that displays information that you're actually calculating, you're inferring perhaps objects on a screen, you can use GPU number 1 to actually render that in a pretty way up on top of the screen. The second GPU can actually run your inference engine. So it's not doing anything on display, it's actually running the neural net. And because they're split, we're not having to do complicated software techniques to take a single GPU and do both actions. We can guarantee the amount of bandwidth we want, that inference engine wants, and we can guarantee to the customer how much performance they're going to get by running on a separate GPU and running the display system on a different GPU.
Great. And you actually touched on something because you said vision processing, and
Absolutely.
these GPUs have another trick up their sleeve because they have VX extensions.
Right.
Yeah. Where do you typically see the use for that vision processing on your devices?
Well, let's talk about why you want to do it in the first place. Common architecture wisdom says, if I'm going to do vision processing, give me a big GPU, run it all on the GPU. Perfectly fine way of doing it. However, the tax is that you're going to have high power, but with that high performance. So one of the things we wanted to do was have a balanced architecture, a balanced power budget, but still be able to do vision across up to 8 cameras with i.MX 8, which requires a lot of bandwidth. That's where the VX extensions come into play. The VX extensions allow us to run single cycle, highly accurate math functions within the GPU itself. Yeah. In essence, it gives us our GPU the performance of more GPU capability with less silicon area and less power. So we can do the same work that a single GPU without VX can do across 8 cameras with a much smaller GPU, which is less costly and less power. Now the VX extensions, from an architecture perspective, one of the key things that we do in automotive, as well as industrial, security, monitoring people, is camera stitching. Yeah. So the idea, if I can have 8 cameras, if I can stitch all views together, then I can see a 360-degree view of my world. From a car perspective, it allows me to do automated backup instead of having to look through a small screen. But you're trying to monitor traffic flows through your store, you can have a 360 camera looking at everybody and be able to count the people, and not only count them, be able to find out which display in the retail shop they're congregating around, which is going to be valuable for the retailers.
Oh, that's really good. And actually, you're showing your surround view stitching from the cameras that you have up there,
right?
And it's running on the same GPUs that are also driving the whole experience here and the infotainment. So all of that running on a single device, 2 GPUs.
And that's where the magic comes in. So right now, we still are, even though it's not being shown, we still are rendering the heads-up display, the cluster, the navigation screen, and we're stitching 4 cameras in real time in a 360 view. All of that is being done across those 2 GPUs, which is a testament to the performance that we can get inside of i.MX 8.
Yeah, and you don't even have an ISP on there, right? It's all on the GPU?
It's all on the GPU. So one of the great things about the VX extensions is that we can do software-based ISPs. So ISPs, for the uninitiated, basically when you take a camera image in, it does dead pixel correction, balances the color, etc. Now, why didn't we put an ISP in the first place? Well, when you commit it to silicon, typically by the time the processor comes out, the features that are needed are obsolete. You need a software-based solution to be able to keep up with what customers are looking for. The second is that the way things work within a car, you typically have long travel distances on your cameras. They typically have smarter cameras on the other side with actual ISPs inside of them, so we don't need an ISP. But in the cases where we do, VX extensions allow us to do ISP work on the same GPU that's doing the stitching and driving 3 screens of content.
Great, thanks. So I'd like to pick your brain a bit about AI processing on the GPUs as well, but I think you have something else that you can show me on that.
Got a lot of demos over. Let's go take a look.
Yeah, thanks.
All right, thanks.
Cal, good to be back. So we discussed i.MX 8 and graphics in general, and then we touched on the point of acceleration of AI, machine learning. So here you have a setup that actually shows what it's usable for. Can you walk me through what you're showing here?
Yeah, first of all, let's talk about the importance of edge computing. So when you think of neural nets, a lot of people will think about cloud. So I'm going to take a set of images, send it to the cloud, it's going to tell me what it is and come down, which is a perfectly fine way of handling it. However, when you start thinking about intelligent devices like we're showing here, intelligent microwaves, intelligent fridge, we actually want to push the intelligence and the machine learning down into the edge node. And what we're showing here today is it's actually an i.MX 8 sitting underneath the microwave. We're going to show you the potential that graphics acceleration, that machine learning acceleration can do for edge computing. So modern microwaves, state of the art. Take frozen food like macaroni and cheese, take a barcode scanner, look up a database that says 5 minutes to cook, throw it in the microwave, and it does its thing. The problem is if you and I are watching the football game or making hot dogs, there's no barcode on this, right? Yeah. So we want to be able to stick a generic plate of food inside of a microwave and be able to have accuracy rates of 99% or higher. So we've been working with our partner Ozone and their tool DeepView RT to be able to create our own training data, our own neural nets optimized for our silicon and deploy it across every single processor that NXP has. That includes our highest end i.MX 8 all the way down to our Kinetis microcontrollers, including our crossover processor i.MX RT. So let's show you a little bit about what the microwave will do. So if I'm worried about weight, and who isn't, at least me, nutrition goals, etc., I want to be able to put food inside of a microwave and say, well, this is going to consume 540 calories. So if I have one of them, and during the game, no big deal. If I have 4 of them, I probably need my Garmin watch to do a 30-minute exercise to run off the calories. So this is an example of edge computing. There's absolutely no connectivity to the web right now. I'm not using a server in the cloud. All of it is running directly on i.MX 8 in real time. So it's inevitable that we're going to stick something in the microwave that it doesn't recognize. So I've got a meatball sandwich here.
Looks delicious.
Right? Stick it inside the microwave, and the neural net actually does a fairly good job. It sees some brown and white and says those are chicken fingers. Now you and I can tell that's the wrong food, so what are we going to do about that? Well, one of the things that Ozone's technology allows us to do is update the model. Now this is pure edge computing. So what we want to do is find somebody else on our local network that knows what that is. Now the update happens pretty quickly, but I update the model, and just to prove that it's live, rotate the food, and now I'm at 99% accuracy on the sandwich. So what happened underneath the covers? The first thing I did was I asked another intelligent appliance on my network, do you know what this object is? It happened to have the classifier, sent it back into the microwave, and that's how this device learns. The second part of under the cover comes back to what we talked about earlier. What we're doing is running the inference engine on the GPU. And we have some timing on that where we're able to get inference of 19 milliseconds running this model with 20 classes. So that allows us to have an intelligence that's inside of the edge that's not dependent on internet connectivity. Second, be able to update it and have it learn over time as you and I have different types of food that we provide into our appliance. And then be able to provide a use that is useful to our way of life. We can actually take information from this, and what's great about it visualizing the food is if you have a gluten allergy, a lactose allergy, or peanut allergy, you need to know if food has been placed inside of this appliance that actually will trigger that allergy and do something about it.
That's great. And I can see in the you're also showing a fridge, so essentially you're scaling up the whole solution here, right? Going from single camera microwave to I think multiple cameras on the other end, and even more processing?
This is just the beginning. This is doing single image, single camera, you said. We're actually using only a fraction of the GPU performance inside of Quad Max to do that. And then in a moment here, we'll show you how we scale it up to multiple cameras like we showed in the previous demos or showcases, and actually use it for machine learning across multiple objects.
Okay, let's have a look.
That's it.
Okay, Cal, so we're looking at a fridge here with multiple cameras, and you're scaling up the problem to the large i.MX 8. Tell me what you've got here.
Yeah, so in this case, unlike the microwave, with the refrigerator, you're going to have multiple objects inside. You're going to have cans of Coke, cans of beer, as well as food and ingredients, right? So what we do is we actually have 2 live feeds coming in. The first is for can counting. So I have a live feed coming in at 1080p, which the GPUs and the VX extensions are processing, using color segmentation to say, hey, I only have 1 beer left at CES. That's a problem. So hit the buy beer button. Once I get it back in, I'm able to get it back up to the proper count. Now, our much harder problem is segmenting food. Unlike the microwave where there's only 1 object, I have multiple objects that has to sit inside the microwave. Now, if you're going to do ingredient counting, that's fine, but if you're coming over to my house for beer, watch the game, you want to be able to create some snacks, and based on the food that you see inside there, have it actually suggest a recipe that you might actually want to be able to have fun with. Now, at the end of the day, edge computing is about taking data in, optimizing it, and running it through neural nets efficiently at low power. And by using the GPU and the VX extensions that we have in i.MX 8, we're able to do that very accurately and get very high recognition rates without hitting the cloud.
Excellent, perfect. Thanks a lot, Kyle.
Thanks a lot,
Good seeing you.
Good seeing you again.